Welcome everyone to the second session of the blockchain course. If you have any questions at any point, please just write in the chat and I would happily answer them. So can you see my screen just to make sure everything is working fine? Okay, great. So in the last session, we ended up talking about cryptographic hash functions, and today we're going to build up on that. So just to refresh your memory from yesterday, a cryptographic hash function, or generally a hash function, is just a function that maps strings of any length to strings of a fixed length n. So I have a function h, and here my sigma is basically 0 and 1. So I always assume that my alphabet is just bits. I can have 0 and 1. And then sigma n is basically all words of length n, all words that have n bits in them, and sigma star is the set of all finite words. So it takes any word or string or file and maps it to a word of length n. And we said that in practice, usually n is 256 or 1024. And then the requirements that we had for it to be called the cryptographic hash function were collision resistance and hiding. We said that this kind of function can never be one-to-one because, of course, I have an infinite domain and a finite codomain. So just by the pigeonhole principle, I would have some items mapped to the same item here. Sorry. But we said that it's collision resistant in the sense that we don't know an algorithm that can actually help us find two different values, x and y, that have the same hash. And we said that our hash functions are also assumed to be hiding in the sense that if I give you the value of the hash function, you cannot find a pre-image that maps to that value. So if I give you y, you cannot find an x such that the hash of x is y. And we said there is another thing called puzzle friendliness, which we will come back to. Now, we talked about some applications of hash functions, and the first application we already saw yesterday was this idea of using hash functions as a digest. So the hash of a file is a very short summary of that file somehow. And I said that if we have a large set of files, large database F of large files, and if I have a new file and I want to see whether it's in the set or not, I can just keep track of the hashes of all the files in my set. And when I get this new file, I also compute its hash and then just search by hash. And we did this analysis and we said, basically, if this fails, it means that we found a collision in the hash function. Okay, now the second thing that I kind of mentioned last session, but didn't really get into, was this idea of using the hash as a pointer. And this is the main theme in the current session. So how do I use a hash as a pointer? Again, I want to remind you how pointers worked normally, like in C++. Basically, the idea is that if you have a bunch of objects, each of your objects is going to be saved somewhere in your computer's memory. So let's say this is my memory. So imagine that this is my RAM, and every byte of it has a number. So this is byte number 0, byte number 1, byte number 2, so on. And let's say I have a bunch of objects. Let's say I have this object A, and I have another object B. And when A points to B, basically the pointer is just telling me where B is stored here. So if B starts at position 100 in my RAM, and if I've put B here in my RAM, then this pointer from A to B is basically just going to save that number 100, right? So normally a pointer is a location pointer. It's pointing to the location in the memory where that item is stored. But we said that we can also have hash pointers. So the idea here is that I don't want to point to a particular place in the memory because someone can change that. Instead, I want to point to a particular object. So instead of saying that I give you a memory location and whatever object is in that memory location, I'm pointing to that, I'm going to say I give you a hash. So I give you the hash of B. And basically, what I'm pointing to is any object that has this particular hash. But of course, that object is unique because I cannot find collisions. So I'm uniquely pointing to a particular object. And then if I have that object B, and if I change anything about B, then the hash of B would change. So these pointers are immutable in the sense that when I point to something, if that thing changes later on, I'm no longer pointing to it. I'm pointing to the original version. Okay. Now, let's see. How does this actually help us? So here's the problem that I want you to consider. Let's say that you have an account with a bank and you do not trust your bank. Okay. And the bank basically sends you emails whenever there is a transaction on your account. So the bank announces transactions by email. Now, if this is the case, if every time there is a transaction on your account, the bank just sends you an email, you can prove the existence of the transactions when you receive the email, right? So we're assuming that the emails are certified and signed by the bank. We will see digital signatures later on. But generally, the idea is that if I've received an email from my bank saying that a particular transaction has happened, the bank cannot later deny that because I can just show the email that I received from them. But the problem is that the bank might claim that there was some transaction. Maybe I spent some money, but I have never received the email for that particular transaction, right? And if that happens, the bank can just claim that, oh, I sent you the email, maybe something is wrong with your email account, maybe you deleted the email, whatever, right? So you want to make sure that the bank cannot do this. So the problem is that we want the bank to basically commit to the history. We want to make sure that the bank cannot change the history. Or actually, I want to say the history is immutable. Okay. How can I do this? Basically, I can use hash pointers to create a linked list. And if I create a linked list using hash pointers, then all of the objects in there will basically have the immutability property that we want. And this is called a ledger, or later on, we will create a blockchain, which is a very similar data structure. So the solution here is a linked list with hash pointers. Now, what do I actually mean by this? I mean this. So let's say I have my first transaction. This is transaction number 1, and it has a bunch of fields. So I don't know, it maybe has a sender, a recipient, an amount. Let's say we have a standard for showing our transaction as strings. Now, the bank just sends me an email with this transaction. Now, the next time that the bank wants to send me a new transaction, so if I have a transaction 2, this transaction is going to have all the information about the transaction, whatever I need. But it's also going to have a pointer to the previous transaction. So I call that P, and it's basically the hash of transaction 1. So transaction 2 is going to point to transaction 1, and the way it points is that it's saving the hash of transaction 1 as a field in there. Okay. So, and then we continue exactly like this. So the next transaction will have all those information as before, and it will also have the hash of transaction 2. So every time that the bank sends me a new transaction by email, it has to also include the hash of the previous transaction. And this continues. Let's say I have n transactions. Okay. And this one will have the hash of transaction n-1. Great. Now, First of all, I want to show you that this has very low overhead for the bank, right? Because every time the bank is sending me an email for a transaction anyway, it's just that in that transaction, they have to include the hash of the previous transaction as well. So every time that the bank wants to send me an email, the overhead is just computing one hash, which is super easy. Now, we want to analyze several things here. First of all, what is the overhead for me as the user, as the client, to verify that the bank is not cheating? So here's the thing. How can the bank cheat? Let's just talk about this. The bank can cheat by trying to change some transaction. And by change, I mean maybe change a field in a transaction, or maybe add a new transaction that wasn't there, or remove a transaction that was there. All of these changes are pretty much the same. So let's say that the bank wants to change transaction I, and I'm going to just do the case where the bank is changing some field in a transaction, but the cases where the bank tries to remove or add a transaction are very similar. So let's say that the bank has already given me a bunch of transactions. So transaction 1, transaction 2, so on. And at this point, it was transaction I. And then there was, of course, transaction I plus 1, which pointed to transaction I, and so on to transaction N, which is the last transaction I have received. Now, let's say that the bank wants to change this transaction. So the bank wants to create a new transaction I. Let's call this transaction I prime. Now, what happens if the bank wants to change this? Well, of course, the bank has to put a pointer to the previous transaction. That's fine. So the bank can create this fake transaction here. But then the problem is that in transaction I plus 1, I had a pointer to transaction I, right? And again, remember that the pointers are hashes. So in transaction I plus 1, I basically had the hash of transaction I. You see, every transaction has a field, which is the hash of the previous transaction. But now, because transaction I has changed, its hash has also changed. Remember, we have collision resistance, which means that the bank cannot really find two different transactions that have the same hash. So whenever the bank is changing the transaction, we assume that it cannot change it to a different transaction with the same hash, because otherwise that means the bank has some superhuman abilities and could actually break the collision resistance of our hash function. So here what's going to happen is that the bank changes this transaction I to this new fake transaction, but then that changes the hash of transaction I, which means that transaction I plus 1 has to change. The field in transaction I plus 1 that contained the hash of transaction I should change so that it now contains the hash of this fake new transaction. But that would change transaction I plus 1. So that means that the bank has to now create a new transaction I plus 1 that points to the fake transaction I instead of the original transaction I. But you can see that the same argument goes through for transaction I plus 2, right? So now transaction I plus 2 was pointing to transaction I plus 1. But because I changed transaction I plus 1, that pointer doesn't work anymore. The hash has changed. So I have to now create a new fake transaction I plus 2, and so on all the way to transaction N. So any change in the history will also change the last transaction, right? But here's the thing. If you're the client, you have kept all the emails from the bank. So you can easily show the bank this last email and show that, hey, you previously gave me this transaction number N, and this doesn't match anymore. The hashes don't match. So the really cool thing here is that as the end user, you don't even have to keep track of all the transactions. You can just keep track of the very last transaction. And you can be sure that if the bank wants to change anything, they have to change everything all the way to the last transaction. So another way of looking at this is that this hash in the last transaction, it's the hash of the previous transaction. So it's a commitment to the previous transaction. It means that no one can change the previous transaction without changing this hash. But that previous transaction itself has a hash to the transaction before it. So it commits to the previous one and so on. So this hash is actually a commitment to the entire sequence, to the entire linked list. If anyone changes anything anywhere in this linked list, this final hash will change. Okay? So that's the idea. And we're going to actually use this to create our blockchain later on. But the good thing here is that if the bank cheats, you can prove that the bank is cheating. Of course, you cannot stop the bank from cheating, but you can prove it. And assuming that this is in a country with a court system, you can go to court and actually show that the bank was cheating. Okay. Now, I want to move forward and show you another application of the same ideas, another application of this commitment to a particular value using its hash. And this is what we call a commit reveal scheme. And this is probably the most common thing we will do in this course. So you will definitely at some point have to implement this as a smart contract. Here's the problem. Let's say that we want to do an auction. So let's say I have N people who want to bid for a particular item. So who bid for some, let's say, valuable item. And let's say that person I's bid is BI. Okay. Now, this is an auction. So I want to make sure that people do not see other people's bids before they make their own bid. So this is the security requirement. I have to require that no one sees other people's bids before making their own bid. Because otherwise, of course, I might cheat. It might be that I'm bidding only $10 for the item, but if I know that you're bidding 15, maybe I want to defeat you and I bid 60. Okay, so that's the one thing. The other security property that I want is to make sure that no one can change their bid. Because of course, otherwise people can cheat, right? What else do I need? I always need transparency. I need to make sure that the end of the process is going to contain a phase where everyone sees everyone else's bid and everyone knows who the highest bidder was. So I have to have some sort of transparency at the end. And by transparency, again, I mean that everyone can verify the results. Everyone can verify that the person who won was actually the person with the highest bid. Okay. And what else do I need? Do I need any other kind of security property here? No, but I have to also say what kind of communication I have. And let's say this is over the internet. So let's say maybe I have a public forum where anyone can send a message to this forum and everyone else can see that this person sent this particular message. Okay, so that's our mode of communication. Now, how are we going to solve this? Now, I want you to just think about this in the real world. And by the real world, I mean the non-digital world. So how do people actually do auctions traditionally? The idea is very simple. Each one of the bidders will have an envelope. They would write their bid on a piece of paper, put it in the envelope, seal the envelope, and give all of the envelopes to some dealer, some organizer of the auction. And then the dealer opens all of the envelopes in front of everyone and shows all the bids to everyone. And then everyone knows who the highest bidder was, right? Now, if you consider this simple protocol with just envelopes and pieces of paper, you can see that it satisfies all of these requirements. So when you're making your own bid, you're just writing your bid on a piece of paper. You have no idea what the other people are bidding, and you put it in a sealed envelope. And when you give your envelope to the dealer, again, the envelope is sealed, so no one else can really see what's in there. And you do this, and then you wait for everyone to give their envelopes to the dealer. And of course, you cannot change what's written and put into the envelope. So you cannot change your bid after you have committed to it. And of course, at the end, you also have transparency, because at the end, the dealer just opens all the envelopes and everyone can verify everyone else's numbers. But how can I do this if we are not in the same room, if we are just communicating over the internet? And let's say, again, we have a public forum. I have a way of sending messages where everyone else can see. Okay, so here's how I can use hash functions here. I say in step 1, each person just hashes their bid. So each person I, let's say, computes the hash of their bid. Okay. And let's call this HI. So HI is the hash of the ith person bids. And then in step 2, they each announce the hash. So every person announces HI. So at this point, everyone knows everyone else's hashes, right? So this means that no one can change their bid. Because if they try to change their bid, again, based on the collision resistance property of the hash functions, they cannot change it so that the hash remains the same. So this announcement is actually a commitment. We're going to call this step the commit step. Because by announcing the hash, they have basically committed themselves to their original value BI. They cannot change BI without changing the HI. But at the same time, it's not leaking any information, right? Because the hash functions are hiding. So all the other people, they're just seeing the hash of my choice. They're not actually seeing my choice BI. So they have no idea of what my actual bid is. They just know that the hash is HI. Okay. And then finally, after everyone has announced their hash, so we wait for everyone to announce. After everyone commits, we finally have the last step, in which they all reveal their values of BI. So everyone announces BI. And we call this step the reveal step. Okay. Now, what's happening here? You see, when I announce my value BI, everyone else can just compute the hash of BI and make sure that it was the exact same hash that I announced in the previous step. And if it's not the same hash, they just know that I'm cheating and they would just exclude me. So let's say I have a verification here where all the other players basically verify. So others verify whether the hash of BI is really equal to the HI that was announced in the previous step. And if it's not, we can have some rules for cheaters. I don't know. We punish them, or we say that the cheater always loses by default or something like that. And then we take the BI values, the bids of all the people who did not cheat, and we say, let's take the maximum, and that's the person who has won the auction. Okay, nice. Now, let's analyze this and let's see if we really have all of these properties. Actually, let me give some numbers to these properties so that I can refer to them. So let's say property 1, 2, 3. So property 1 was that no one sees other people's bids before making their own bid. So here's the thing. When I'm making my bid and announcing it, honestly, it might be that I have already seen some of the other people's hashes, some of the HIs of the other people, right? Because even though the protocol says you should first compute your hash and then announce it, there's no way we can enforce that people are actually doing that. So all we can do is to have some time period saying that you can announce in this particular time segment from this deadline to this deadline, right? So, and it might be that when someone is announcing, someone else is looking at what they're announcing, the hash that they're announcing, and tries to maybe open the hash and based on that change their own value. But generally speaking, I only know the hash of the other people at most when I'm trying to choose my own value. So that means that because the hash function is hiding, I don't have any information about the actual values. So since the hash function is hiding, no one can compute BI based on HI. Okay. So we're using the hiding property for 1. Now for 2, we say that no one can change their bid. And basically, to be more specific, no one can change a bid after they have committed to it, after they have announced their hash. And again, this is kind of obvious because when I announce my hash, if I try to change my bid, I have to change it in a way that keeps the hash the same, right? Because otherwise, in the next step, when I reveal, if the hash does not match, then I just lose the game. So I have to find another value that has the same hash, but the hash function is collision resistant, so I cannot find 2 values with the same hash. So in 2, I'm basically using the collision resistance property. Okay. And finally, we say that we have transparency at the end, meaning that everyone can verify. And that one is pretty obvious because in the end, everyone is announcing their bid and everyone is verifying everyone else's bid. So of course, there's transparency. And of course, you can check if someone has cheated or not by just checking that they have the right hash. So part 3 is trivial. Okay, now there is a problem with this protocol. Can you see the problem? Can you see the security vulnerability here? So try to be adversarial and try to attack this protocol. If you want to attack, how would you attack it? Again, let me show you the protocol one more time. So this is my commitment scheme or commit reveal scheme. How would you attack this? Yes, okay. In the chat, there's a great question. Does the BI have a set form? Well, the BI is an integer, right? The BI is just the bid of person I, like how many dollars I want to bid. And yes, exactly what we have in the hash. Great. By the way, I don't say your names because I don't have your consent to have your names in the YouTube videos. So sorry about that. But yeah, so the whole point here is that suppose I'm bidding for an item, and let's say this item has a worth of roughly $1,000. So people are probably going to bid somewhere between, let's say, $500 to $1,500. I have a range, right? And this range is usually small. So I can actually try every possible BI in this range. So when someone announces their hash, even though the hash is supposed to be hiding, and it is, of course, if you have a huge domain, what's happening here is that someone has announced HI, but I know that HI is the hash of something between, let's say, 500 and 1500. So I can just do a brute force. I can compute the hash of every value, 500, 501, 502, all the way to 1500. And then when I see the HI, I can just check which hash is this. And that would already tell me what the value of BI was. So actually, we don't have this property. We don't have the property that no one can compute BI based on HI because our approach is vulnerable to a brute force attack. Okay. So I can basically try all the possibilities for the BI. Now, how do I avoid this? I avoid this by making sure that the domain is bigger. So the problem I have here, the reason why people could open my hash by brute force is that BI could only take, let's say, 1,000 or 1,001 different values, right? Because it could only take very few values, people could just brute force all the possibilities. Now, I want to intentionally make it such that whatever I'm putting in my hash function can take many different values. So this is what we call salting or noncing. And basically the idea is, again, extremely simple, but very elegant. So here's what I'm going to do. I'm going to say each person is going to first choose a random number. Okay, chooses, or a random string, let's say, a random string. And I'm going to call this random string NI. Okay, now, this random string is often called a nonce or sometimes a salt. And it has to be long. Okay, so let's say this is long. In practice, let's say it's like 1024 bits or something, or maybe even longer. Who knows? Let's say it's 2 to the power of 20 bits. I want it really long. So generating a long random string is not hard. And then here's what I'm going to do here. When I'm doing this, when I want to compute the hash, I don't just compute the hash of BI, I compute the hash of BI concatenated with NI. Okay. Now, you see what's happening here? No one can brute force this anymore, because no one can try all the possible NIs. Even if the BIs have a very small range, very few possibilities for BIs, there are many possibilities for the NIs. So the hash that I'm giving is actually really hard to invert now. Now, again, in practice, maybe 2 to the power of 20 is overkill. Maybe you can just do 256 bits. It's up to you, like what's considered long for you. Now, of course, I have to also change this step when I'm announcing my value, because instead of just announcing my bid, I have to also announce my salt. And then here, when they want to check, instead of just checking the hash of the bid is HI, they have to check that the hash of the bid and the salt is equal to HI, right? But this makes it so that this domain here, like the possible values of BI and NI, is huge now. So I have 2 to the power of 256 different values for NI. And now no one can do brute force. So this is no longer vulnerable to brute force. It was vulnerable to brute force only in the absence of nonces. So yeah, the lesson here is that you should always add a nonce when you're using hashes for commitment. Okay. And actually, it makes sense to even add nonces in a lot of protocols like this as well. Okay, great. Any questions about this? Okay. Yeah, so let's talk about another application. So here's what I want you to consider. Let's say there is a bank that has two different branches. So let's say I have a branch here in Hong Kong, and let's say there is another branch in, let's say, London. Okay. Now, consider that these are in the old days and people are just going to use things like traveler's checks, okay? So I have a bunch of people who are depositing money in this branch. So maybe Alice deposits, let's say, $100, and then maybe Bob comes in and deposits $50, and so on. Okay. So I have a bunch of deposits. And they deposit in the Hong Kong branch, but they want to later on go to the London branch and receive their money there. Now, the problem is that they have to somehow be able to prove to the London branch that they have actually deposited something in the Hong Kong branch, right? Now, again, in the old days, before the internet and before computers, of course, they could just get some sort of a receipt or some banknote from the Hong Kong branch. And the idea was that it has to have some sort of security property that makes it hard to forge. And then they would take this proof to the London branch. And whenever they show the proof, the other branch knows that they have actually deposited the money somewhere else. Yeah. So the idea, again, is that whenever someone deposits money, so Alice is giving money to the Hong Kong branch, the Hong Kong branch has to give her a proof. And this proof is what Alice can use later on to convince the London branch that she has actually deposited money in Hong Kong and she should be able to get it back. Now, in our situation, we want to have something similar, but of course, we want to have it in a more digital way. And also, we assume that the Hong Kong branch can send a message to the London branch. Okay. So let's say, again, this is the pre-internet days. They can send a fax message, let's say. But the problem is that the communication challenge that the communication channel that they have is unsecure. So again, imagine the old fax machines, anyone can listen in. So whatever message the Hong Kong branch sends to the London branch, it's not going to be private. Anyone can see this message. And let's say that this message is also expensive. Okay. So we want to send the shortest possible message. We don't want to really send a long message because it's expensive to use it. Again, just think of the old fax machines and imagine that this is like an international call. So it's really expensive in the 1980s. So let's say I want to send a message, and this message, I'm going to call it M. Okay. So you see there are several parts to this. There is the message that this branch sends to the other branch, but there is also the proof that this branch gives to any of the customers. And then let's say the next day or the next month, whatever, after some amount of time, each of the customers should be able to go to the London branch and give them the proof. Let's call this proof P. So Alice gives the proof P to the London branch. And then the London branch should be able to verify this proof using the message M that they got from the Hong Kong branch. Okay? So that's what we need here. How can we do this? So what should the message be? What should the proofs be? And okay, so the requirement additionally is that we require privacy. And what I mean by that is that I want to keep the identities of the customers and the amount of money that they deposited as a secret. I cannot include that in M. Because if I put the identities in M, then maybe I get hacked. Again, this is an unsecure channel. So those identities will be leaked. Generally, anything that is sent over this channel will be leaked. You have to assume that everyone in the world knows M, because if a hacker knows it, maybe the hacker just publishes it and then everyone else knows it. Okay. So I cannot have a situation where the Hong Kong branch simply just sends a list of all the people and their deposit amounts to the London branch. That's not going to work. Okay. Now, a very simple thing is to use no proof at all, right? So the Hong Kong branch can just take the hash of each deposit and let's say just sends that hash to the London branch. And then as the proof, we can actually use like the deposit itself or nothing at all. Well, basically Alice goes to the London branch, says, I'm Alice, I've deposited $100 and just take the hash of this string, Alice and $100 and see that the Hong Kong branch has sent you that hash. Of course, here again, we have the problem that someone might brute force the hash. So we have to add some salts. And then we can say that the proof is the salt, right? So this is our first attempt. Is that we say for every transaction, the bank or the Hong Kong branch sends the hash of that transaction and some nonce. So actually, let's call it transaction I, the hash of transaction I with some nonce to the London branch, right? And then the proof that he gives to the particular customer is just the transaction and the nonce. So, and again, this nonce is a long random string chosen by the bank. Okay. So the customer can go to the other branch. They can just show this transaction and the nonce. The other branch can compute this hash and just check, is it one of the hashes that I received from Hong Kong? And if so, then I would pay it. And of course, we have to make sure that we do not double pay. So we not only require privacy, we also require that anyone who deposits money can get their money back, and they can get their money back exactly once. So every deposit can be reclaimed and cannot be reclaimed twice. But this is also easy. So the London branch can just keep track of all the hashes that have already been paid and wouldn't pay twice for the same hash, right? That's easy. But the problem, again, is that we said this channel is expensive. And since this channel is expensive, I don't want to send a different hash for every transaction through this channel, because if I have n different transactions, I'm basically sending ON or actually theta n messages here, and it's expensive. I don't want to pay that much. Can I send a much shorter message? And again, the answer is yes. This is actually going to be our second attempt. So our second attempt is to basically just use a linked list with hash pointers. So the bank is going to do this. It's going to create transaction 1, and then it's going to put transaction 2 here, but transaction 2 is going to include a pointer to transaction 1. So again, transaction 1 has a name and an amount, but transaction 2 has a name, an amount, but also the hash of transaction 1. Okay, let's call that P. And then the next transaction will have a name, an amount, and the hash of the previous transaction. And this will continue. So we can assume that all of the transactions are done in the morning. So all the customers go to the bank in the morning and deposit all of these things. And then the bank creates this, let's say, ledger in the afternoon. So the bank creates this. And again, now remember that the hash of the last transaction, the hash of this transaction N, is basically a commitment to the entire sequence. So the bank can just send the hash of this transaction N. The Hong Kong branch can just say my message to the other branch is simply the hash of the last transaction. And this hash is, of course, of a fixed length. We said that it will just have a length of 256, right? Because that's the definition of a hash function, that it maps strings of any length to strings of a fixed length. So now the message that I'm sending has constant length. It's just O1, right? But now what kind of proof should I give? So let's just consider this very simple case where I have exactly these 4 transactions, right? So let me zoom out a little bit so that I can see them. This is what's going to happen. I have my transaction 1, and transaction 1 basically has Alice's name. It has the amount in it, and it doesn't have any pointers. So it's just this. And then I have another transaction, transaction 2, which has Bob's name in it. It has the amount that Bob paid, which is $50. But it also has a pointer to the previous transaction. So it has the hash of transaction 1. And then I have transaction 3. Very similar. Like I have Carol. She's paying $200. I also put the hash of transaction 2. And finally, I have transaction 4. And here I have Dave, 3,000. And I have the hash of the previous transaction. Now, what is the proof that I have to give to people? So each one of these customers, when they go to the London branch, they have to be able to prove that they made this transaction, that they actually deposited this amount in the Hong Kong branch. Now, in case of Dave, the proof is actually quite simple. I just say, bring your transaction, bring this whole thing, transaction 4, to the other branch. And then the other branch just looks at the hash and realizes that this was exactly the last hash that I received from Hong Kong. So they know that this transaction happened, and they know that this is the last transaction, right? But the problem is what happens with Carol. So Carol has a huge problem, actually, because if she wants to prove that her transaction is there, she has to also prove Dave's transaction, right? So the other branch only knows the hash of the last transaction. So in order for Carol to prove that her transaction was somewhere in the list, she has to first prove Dave's transaction and then show that there is this hash pointer, the pointer to transaction 3 in Dave's transaction, and then show that her transaction has that hash. So the proof that I'm giving to Carol would be her own transaction, but also Dave's transaction. And then the proof that I give to Bob would similarly need to include Carol and Dave's transactions, and so on. Generally, if I want to prove transaction I have to give all the transactions that come after transaction I. And this is terrible for privacy, of course, because now I have a situation where some of my clients know about the transactions of other clients just because those transactions came after theirs. And also, it's really bad in terms of the proof lengths. So right now, we're just sending this message M, which is 1 hash. It's just the hash of the last transaction. So we saved a lot of money here. This channel was expensive. I'm sending only 1 message there. But the trade-off is that the proof that I'm giving to each one of my customers is actually getting quite long. So it's not a problem for Dave. It's not a problem for the last guy, because he's just giving a proof of one transaction. But if you look at Alice, she's the very first transaction, so she has to include the proofs of all the following transactions, which means that, like, in the worst case, if I have n people, my first transaction, the customer of my first transaction has to actually give a proof that has a length of n. And of course, these are both really big problems. The privacy problem is a bigger one, but I also want short proofs. So I'm just going to end this session by writing my wish list, and then tomorrow, hopefully, I will get my wishes. So this is my wish list. I want shorter proofs, and I also want privacy. And by privacy, I mean no one sees anyone else's identity or transaction. This is what we will do in the next session.